José Almeida, from Polytech of Portugal, with another work, the comparison manual and automatic tuning of differential evolution strategies for energy research management optimization. José, please.
I think there's no need for an introduction. So I'll be presenting another work called Comparing Manual with Automatic Tuning of Differential Evolution Strategies for Energy Resource Management Optimization, which is basically the same, not the same problem, because this problem, there is no uncertainty, but in this problem, we introduce the network constraints, the power flow constraints, etc. So it is a non-linear problem. In the other one, it was a linear problem. This one is a non-linear problem with more constraints and more variables. So it is still a complex problem to optimize. And this is based on the work done by the second author, Fernando Lezama, which he implemented these differential evolution strategies, but it did it with the manual tuning. And then I took this and I wanted to improve the results that he achieved with an automatic tuning. So the same thing, I'll be presenting a small introduction, the methodology, the different differential evolution strategies, our automatic tuning method, which is the uniterated F-race method, in short, irace. Then I'll be presenting also a case study where I implemented this, the parameterization needed for irace to tune the parameters, and then some results and some conclusions. So again, because it is a similar problem, the energy resource management problem, again, is becoming more complex with the penetration of distributed resources, which means a high dimension with a high number of variables to optimize, a large number of constraints, and also uncertainty. In this case, as I said, we do not consider uncertainty, but we do consider the non-linearities of the network. And then we implement, again, in this case, a small part of the meteoristics, which are evolution algorithms, because meteoristics is basically a group, and we have here evolutionary algorithms. These are good algorithms. There's multiple literature with these algorithms that offer good solutions in useful computational time, have a low computational effort. As I previously showed, vortex search was a very simple algorithm to implement, but yet very effective, and are of easy implementation. These are population-based methods. That means that we have multiple parameters to tune, to optimize, so good solutions are given, because these parameters influence the solution. So we need to fine-tune these parameters to achieve feasible and good solutions to a wide range of problems. So we need to achieve some sort of robustness in the algorithms. So we present an automatic configuration of these algorithms for a centralized energy resource management problem in the day ahead. So again, we need to optimize a fitness function. In this case, our fitness function is we have a centralized EI.A energy resource management. So we assume that an aggregator has control over the resources of our network. So we want to maximize the incomes. The incomes are basically given from the energy storage systems and the electric vehicles charging revenue and the market revenue. And we want to minimize the operational costs. So we want to minimize the expenses from generation costs and also the discharging costs of storage systems and electric vehicles, the demand response as well, the incentives for demand response, and the energy not supplied. Here are the constraints of the problem. In the paper, I have I have the formulation for these constraints, so you can check it out if you want to see the mathematical formulation. So these are the differential evolution strategies that my colleague Fernando implemented initially. Basically, we have what we call the standard differential evolution, which is basically a linear combination of 3 random individuals from the population. And the last two are multiplied by a scaling factor. Then we have another differential strategy. In this case, we take our initial solution, what we call the target vector, and then we sum it through the another scaling factor, and minus the difference between the best solution found so far minus our target vector, and then the same operation that we did in the standard. Then we have two other differential evolution strategies. You can check it out. First one, the third one uses a random variation factor, and the last one, it basically is a random selection between the standard differential evolution and another strategy. So for this automatic configuration algorithm, we need to create a scenario. In this scenario, we set the maximum number of experiments, because this algorithm, the iterated F-race, is basically iterates through the configurations, through the multiple configurations. It's a heuristic method, so it tests random configurations, and then he evaluates those configurations and discards, through a statistical test, discards the worst configurations. Then we also need to set the parameters that we want to tune. In this case, we set the differential evolution parameters. We need an initial configuration that the algorithm starts from. This configuration can be chosen randomly, or can be, if you have some knowledge, you can put that configuration. And then some forbidden configuration, something that the algorithm cannot combine in the parameters. Then we pass it as well the multiple different strategies. The irace algorithm will call a target runner through the configuration and an instance. An instance there is given by a characteristic to a problem and a random seed, and it will return. It calls also our fitness function, and then it will return the cost value and that instance. And in the final, we have the best elite configurations. So again, we tested, this is a realistic distribution network. It has 33 buses, 1,800 electric vehicles with discharging capabilities, 67 distributed generators, 10 external suppliers, 15 storage systems, and 32 residential consumers. So for the scenario configuration file, we set the parameters that the algorithm needs to tune. So in this case, the differential evolution works with a population size, a maximum set of iterations that the algorithm will iterate through, and a scaling factor that we saw in the previous mutation strategies, and also a crossover probability. Then we also set an initial configuration. This was a random initial configuration that we set in the algorithm. Then we also put the training instances for the algorithm to run through, and then a maximum tuning budget, and a forbidden configuration. That in this case, we did not have forbidden configurations. These are also, it also needs the types of the parameters. In this case, these are integer parameters, and these are real parameters that vary between 0 and 1. So when it comes to the tuning experiments, as you can see in green, it's the elite configuration. Here, because the algorithm reached its tuning budget, it did not test this configuration in the two remaining instances. So this value could be worse than this one, or it could be better, but we don't know because the algorithm stopped. And for the first strategy, the best configuration was configuration number 24. We will see the values of the configuration. And then for the second strategy, the best configuration was configuration 49. As you can see, we only have here one elite configuration in the final iteration of the algorithm. For the other strategies, the same thing. For the third algorithm, configuration 27 was the best, and here configuration 52 was the best. So there are the configurations that were given by the the algorithm, because in the previous work, a number of maximum of 60,000 fitness evaluations were tested. We needed to update the second parameter because we only tested for 10,000 fitness evaluations, not 60,000. So we needed to upgrade this value because testing for 60,000 in the irace, it took a little bit too long. So we ran for 10,000 and then through a simple rule, we updated to 60,000. So with the previous algorithm, I basically improved the results for the first three strategies compared to the previous work, except for the last one. So there's still some work to be done here. So to conclude, we applied an automatic configuration method through an iterated f-race approach. We achieved mostly better optimization results, considering the configurations given by that algorithm in comparison to a manual tuning. The manual tuning, basically, you have a set of a range. For example, you test from 0.0, 0.01, 0.01, you go adding. For example, for the number of iterations, you add 10, for example, 10, 20, etc. No, this is basically tests randomly, and it chooses the best one. So it also is less time consuming. So for the first three strategies, we increased the profits from the aggregator, except for the last strategy. Here, we could increase the maximum number of experiments, but we will also increase the computational time because the algorithm will iterate more and it will run more configurations, but will also consume more time. So, for example, for future research, we could do this. We could also provide a good initial configuration because the first initial configuration that we give to the algorithm was basically a random configuration. So if you have knowledge about the problem and what configuration works best, you could provide that configuration. And also we could implement more instances to the problem, so the algorithm could be even more robust. Again, my biography is so that, and that's it. Thank you.
Thank you, Jose. Some question from the audience? No? I just would like to elucidate more about the prohibitive conditions that you put in the algorithm. Is this like some allocation, prohibitive?
So these forbidden configurations, in this case, we did not have any. But for example, we could put that, for example, this parameter times this parameter cannot be less than 20 or something. Those are forbidden configurations that you can set. So conditions that you can set at those parameters, then the algorithm will know, okay, this times this will not work, and then it will not test that. That's basically it.
Understood. No question? So thank you again, Jose.
Thank you.